Keyword search falls apart when the query and document are in different languages. Multilingual-e5 FAISS lets you retrieve across languages in Python without separate indexes. This is the setup you'll be able to run after this, which indexes multilingual texts into one space and retrieves the best cross-language match for an English query. I'm Professor Pi, teaching search and IR with simple Python. Imagine you run a global help desk. Users submit questions in English, Japanese, Spanish, and Arabic. Your knowledge base has answers in all those languages. Keyword search finds exact words, so it misses perfectly relevant answers in other languages. Cross-Lingual Semantic Search solves that pain. It maps text from different languages into the same vector space, so semantic similarity beats exact word overlap. Success looks like a single index that returns useful documents regardless of language, fast enough for interactive use. At a high level, the trick is two parts. First, use a multilingual encoder that outputs vectors where similar meanings land close together. Second, use an efficient nearest neighbor engine to find those neighbors quickly. That gives you one searchable space instead of one index per language. Strengths are simplicity and single-shot retrieval. Weaknesses include model bias and embedding cost at scale, which we will touch on later. We will build a tiny demo that shows the failure of lexical matching, then replace it with Multilingual-e5 embeddings, and finally use FAISS to make retrieval fast and updatable. You will see how an English query can pull a Spanish or Chinese sentence as the top hit. Now we'll run a simple lexical overlap test. This snippet quickly tests how brittle lexical matching is across languages. We build a tiny multilingual corpus with Spanish, Chinese, French, and English entries in the list named docs. The variable Q holds an English weather query. Then tokens and ES tokens are created by lowercasing and splitting on spaces. We compute the intersection size between the English query tokens and the Spanish document tokens to simulate a naive lexical match. Because the languages differ, the overlap collapses to zero despite clear semantic relatedness. The printed overlap demonstrates why monolingual or lexical-only retrieval fails in cross-lingual settings. Next, we swap lexicons for dense vectors from a multilingual encoder. This example replaces lexical overlap with dense embeddings from Multilingual-e5 using SentenceTransformer.encode. We create QVec by prefixing the English query with query per E5 instructions and turning on normalize embeddings for cosine-ready vectors. The list dtexts applies the passage prefix to each document text. Then dvex holds their normalized embeddings. We compute scores as a matrix vector product between dvex and qvec, which corresponds to cosine similarity due to normalization. The index I of the maximum score identifies the most relevant language entry for the English query. Increasing corpus diversity can change which language wins top rank. Normalization keeps scores comparable. The printed top language and score demonstrate shared space alignment. Now we wrap those vectors into a fast nearest neighbor table. This code places the Multilingual-e5 document vectors into a FAISS IndexFlatIP for fast cosine style search. We read the embedding dimension from dvex and construct IndexFlatIP, which uses inner product. Because cosine similarity equals inner product for unit length vectors, we call FAISS.normalizeL2 on both dvex and the reshaped QV query. Adding vectors with index.add registers them for search, and index search returns distances d and indices I for the top results. The top index maps back to our docs list to recover the winning language. If you increase the requested top K, you will see more candidates and potentially different cross-lingual mixes. The printed top language and score confirm FAISS reproduces the dense ranking. Next, we show how to add new passages without rebuilding the whole index. This snippet shows how to update the FAISS index online by adding a newly arrived passage. We append an English weather sentence to the docs list and compute its embedding with SentenceTransformer.encode using the passage instruction and normalization. The vector is L2 normalized for cosine equivalent inner product and then added to the existing index with index.add. We immediately search again with the cached QV query to see how the ranking shifts after the incremental update. Larger batches can be added similarly, and adding highly similar entries typically increases the top score. The printed index size and new top language confirm that dynamic updates change retrieval outcomes. Finally, we package the flow into a single search call for reuse. This example wraps the workflow into a simple search function that pairs Multilingual-e5 encoding with FAISS retrieval. The function search builds a normalized query vector with SentenceTransformer.encode, then calls index search to get the top K neighbors, and returns their languages with scores. We pass an English query about semantic versus lexical matching to test cross-lingual behavior over our multilingual corpus. The resulting list shows which languages dominate the top ranks and the strength of the best hit. Increasing K surfaces more cross-lingual diversity. Decreasing K forces a sharper focus on the strongest candidate. The printed languages and best score provide a compact, end-to-end baseline signal for cross-lingual retrieval. In a production pipeline, you would replace the tiny docs list with your document store and persist the FAISS file for quick restarts. You would also batch embed new passages and periodically re-index if you switch encoders. This demo maps directly to those steps and shows the core behavior you can expect. Recap: Cross-Lingual Semantic Search maps multiple languages into one vector space, so meaning, not words, drives retrieval. Use it when users and documents span languages and keyword matching fails. One caveat: embeddings cost compute and can reflect model language biases, so validate on your data. Next step: tune FAISS parameters, or switch to an IVF or HNSW index for larger collections. Start by experimenting with FAISS nlist and nprobe to trade query speed for recall on your corpus. If practical IR and multilingual search help you, subscribe and watch the rest of the IR videos.